Hi, good morning, everyone. My name is Dayong from the University of Technology, Sydney. So today I'm very happy to share our recent research here. And our research is about reinforcement learning, which combines the reinforcement learning and machine learning. So machine learning is a process of selectively removing some specific set of data from a well-trained machine learning model, and it can ensure that the model will behave as if these unlearned data has never been used in the training process. And reinforcement learning is another set of is another type of machine learning where an agent learns to make the decisions by interacting with an environment to maximize its cumulative rewards. So specifically, the agent will observe some states from the environment, and then it will take some actions against that environment. And then the environment will send some feedback in the form of rewards to the agent. And based on the rewards, the agent will adjust its behavior to refine its decision-making strategy. Now, when the machine learning meets reinforcement learning, it creates a new concept. We call this reinforcement learning. So reinforcement learning enables an agent to forget its training environments, including all the previous learned behavior and experience and all the knowledge. So the result is the agent will behave as if it enters this environment for the first time. So the motivation of this work includes three aspects. First, it aligns with the policy regulations such as GDPR to enable the users to request their data to be removed from the agent. And then the second one is that it can it enables the agent to remove the incorrect and outdated information from the model. And finally, it adapted the agent to any changes that some learned information has become irrelevant or the sensitive. So now we define the problem. So first we define the learning environment as a tuple M, which includes 4 components: a set of states, a set of actions, a transition function, and a reward function. And we also define a set of learning environments from M1 to Mn. And we also denote the target on learning environment as Mu. So the problem is, given a learned policy pi, how can we update the pi to pi prime such that the accumulated rewards received in the unlearning environment is minimized, but the rewards received in the other environments remain the same? So so basically, the aim is to forget this unlearning environment, but maintain the agent's learned behavior in other environments. To address that problem, we propose 2 methods. The first one is a decremental RL-based approach. It includes 2 steps. So first, the agent will thoroughly explore the unlearning environment to collect a sufficient number of experience samples. And then in the second step, the agent will be fine-tuned in the unlearning environment using the collected experience samples with the proposed loss function. So this loss function, in this loss function, the first term guides the new policy pi prime to work efficiently in the unlearning environment, and then the second term encourages the new policy pi prime to have the same performance as existing policy in the remaining environments. So this approach tries to gradually erase the agent's learned knowledge in the unlearning environment. And the second method is a poisoning-based approach. It includes 3 steps. First, it applies a random poisoning strategy to modify the transition function of the unlearning environment, and then the agent learns in this modified environment to learn new policy. And based on the agent's learned new policy, we update the poisoning strategy and then repoison the unlearning environment. So this approach encourages agents to learn some new but incorrect knowledge to forget this unlearning environment. We give more technical details for the second method. So first, we modify the transition function TU by using poisoned transition function TU head. This means that when the agent takes some action A in state S, the agent will observe a new state S hat prime instead of S prime. And then we like retrain this agent in this modified environment using the poisoned transition function. And then based on the learned policy, we update the poisoning strategy, use the proposed reward function. So this reward function first quantifies the difference between the learned policy and the existing policy. And then it combines the rewards received by the agent in the remaining environments when using the current policy pi. We now compare the two approaches. So the first approach, the decremental RL-based approach, it directly adjusts the agent's policy. And then it basically relies on fine-tuning the agent's policy without modifying the environmental dynamics. By comparison, the second approach, the poisoning-based approach, it directly modifies the unlearning environment. So it's more like computationally intensive than the decremental RL-based approach because it includes an iterative process of adjusting the poisoning strategy to modify the unlearning environments. But at the same time, the poisoning-based approach is usually more effective than the decremental RL-based approach because it directly targets at the environment's underlying structure to ensure a thorough unlearning process. To evaluate the two methods, we used three platforms. The first one is the Grid Vault, and the second one is the Virtual Home, and last one is the Maze Explorer. And we also proposed two baselines. So the first one is learning from scratch. So this is akin to the general machine learning. So for this method, the agent will be retrained in the remaining environments. And the second baseline is the non-transfer learning from scratch. So this method retrains the agent in all the environments, including the unlearning environment. But when we retrain the agent in the unlearning environment, we will use an inverse loss function to minimize the agent's cumulative rewards. This is the general results. So we can observe that after unlearning, the agent's performance in the unlearning environments reduces when using both proposed unlearning methods, which is evidenced by more steps to complete the tasks and fewer received rewards. This is another set of general results. So when taking a closer look at the first pair of bars in each figure, we can see that before unlearning, the agent receives high rewards and uses few steps to complete their tasks. Then after unlearning, the agent performance declines significantly with increased steps and reduced rewards. So this means that the proposed methods focus only on the unlearning environments without compromising the agent's learned behavior in the other environments. Now the adaptability study. So the left figures include the results of the proposed two methods in different environment size. So we can see that with the increase of the environment size, the difference in both steps and rewards is magnified for both methods because the larger environment size will introduce additional states for the agent to navigate, and this will make the unlearning task more complex, as the agent has to modify its policy to adapt to the enlarged environment. And the right figure indicate the unlearning results of the two methods with different environment complexity. So here the complexity is represented by the number of obstacles within an environment. And we can see that the unlearning results of the two methods remain very stable because both methods focus on the policy adjustments according to the transition function instead of the number of obstacles within an environment. Now the computation overhead. So in this table, we can observe that both proposed methods are much more computationally efficient than the baselines due to their less exhaustive exploration of the environments. And the last one is the privacy study. So this study is conducted by using the recommendation systems. So in this table, we can observe that before unlearning, the recommendation policy for the unlearned user can be as high as 92%. But after unlearning, the accuracy is significantly reduced to around 68% and 64% for both for the two methods respectively. And at the same time, we can see that for the remaining users, their accuracy and rewards remain almost unchanged. So this indicates the efficacy of the proposed methods. Finally, the conclusion. So in this paper, we propose a new concept, reinforcement learning, which can be used to protect the model owner's privacy and the environment owner's privacy. And to address this, we propose two unlearning methods, which are decremental RL-based and poisoning-based approaches. And we conduct extensive experiments to evaluate their effectiveness. And the results indicate that both methods can like successfully degrade agent ability in the unlearning environment, but preserve its learned behavior in other environments. Yeah, that's all from me. Any questions?
Hi, I actually have two questions. So the first question is, why do you formulate the reinforcement learning, reinforcement unlearning problem as a minimization problem? Because if I want to unlearn my experience from a certain environment, MU, it does not mean that I want to minimize my performance there. Just I forget that I have learned there, not necessarily to perform badly in that environment. So that's my first question. My second question is, in your poisoning-based strategy, why did you change the next state in the transition function instead of poisoning the reward?
So for the first question, I use an like a motivating example. So, for example, I'm quite familiar with here, so I can easily find like everything here. For example, in this city, I can easily find like any landmarks here. So basically, if I forget this city, so I'm usually hard to find them. So it's different from the like traditional machine learning. So based on the paper we defined it, we perform like deterioratively in the unlearning environment.
Okay, thank you.
Okay, for the second question, I haven't tried poisoning the reward function. So our basic idea is to change the unlearning environment and to enable the agent to learn new but incorrect information. So the straightforward is to we add some fake obstacles like in a greater world. So the agent still learns the information, but that information is not correct.
Okay, misleading.
And still in order to to reduce the agent performance.
Okay, thank you.
We have time for one quick question. If anybody has one. Okay, let's thank the speaker one more time. Thank you.